Hello everyone. Uh, uh, Welcome to the 60 digital design and computer organizations laboratory, which I am discussing the fifth question, which is design Verilog HDL to implement decimal adder. A decimal adder is also a BCD, and BCD is also decimal adder and it goes like module decimal adder of a comma b comma sum input of 3 is to 0 a, input 3 is to 0 b, output 4 is to 0 sum. So assign sum is equals to a plus b and end module. Here we are, as we know in the Verilog, it is we want to assign something. We will use assign keyword sum. As we are assigning sum is equals to a plus b, and here we will give the 4-bit order as input and 5-bit order as output. We will get some will be in 5-bit order, and so we will give the input as 4-bit order. And we we here we will, for example, we will take 6 and 9 as example. We will perform the addition of 6 and 9. We will give 6 as input A, which is 0, 1, 1, 0, and we will give 9 as input B, which is 1, 0, 0, 1, and the output will be 15, which is in binary. We know that 0, 1, 1, 1, 1, and we will get it as it is in binary. And the output, for output we will first have to check the value radix to unsigned decimal. We must convert it to unsigned decimal, and then we want to perform the operation. We will now first value will be 6 and 9 and 6. We want to give first 9, and we want to give next 6. Then we will get the addition of two numbers as 15, which is represented in binary as 0, 1, 1, 1, 1. Thank you everyone. Uh,
Hello everybody, this is Kirtan from JNN College and today I am here to explain about DDCO Lab Program 6. It's nothing but a multiplexer. A multiplexer is a combinational circuit that selects binary information from one of many inputs and directs to it a single output line. Normally there are 2 to the power of n lines, selected lines, and n selection lines whose bit combination determines which input is to be selected. And there are different types of multiplexer, and some of them are 2 to 1 line multiplexer, 2, 3, 4 to 1 line multiplexer, and 8 to 1 line multiplexer. Let us now study about 2 to 1 line multiplexer. In 2 to 1 line multiplexer, it connects one of two 1-bit source to a common destination. And the circuit has 2 data input line and 1 output line. And this is the module which have been taken MUX, as I have given the name MUX, and S and D are the input and Y will be the output. Input will be the ratio 0 is to 0, as it S stands for selector and stands for data input. And input D, which do have the in the ratio of 1 is to 0. And output, as I have said here, output will be the Y, and output is stored in the REG, reg Y, and always at SOD. SOD is nothing but the condition which have been taken here as the inputs to both inputs S and D. And let us check for the case S. In the case 0, as Y directs for the D0, and in the case 1, Y directs for the D1. And in the end, case will be finished at here, and module will be get closed. Program will be finished. And 4 to 1 line multiplexer. In 4 to 1 line multiplexer, in which it do contains of the 4 inputs, whereas we will get the 1 output line. And here the module I have taken the name as MUX. S and D will be the input and Y will be the output, whereas S stands for the selector and D stands for the data, Y will be the output. Here input S will be the ratio 1 is to 0, and data input D data will be in the ratio 3 is to 1, and output Y, as I have mentioned earlier, output will be the Y, and the y as is stored in the reg, reg, so have been taken as reg y. Then in order to check the condition, so I have taken always at S or D. Here the condition S or D, in here in the condition we need to check out, and in the case 0, case 0 y will be y, the output y will with the data of 0, and output 1 with the, in the case 1, output y with the with the data 1, and in the case 2, in output y with the data 2, and in the case 3 with the output y with the data 3, and in the case gets closed and end module. And here, as we know, I have divided it into, as this is the 4 to 1 line multiplexer, we have divided it into 4 parts, whereas here we can see it do contains of 4 inputs and 1 output line. And as you have divided it into 4 parts, as it stands for 0 to 0 and 1 to 1, so we have directly taken it as f equals z, and here 0 to 1 and 1 to 0, so we have taken f equals z bar, z dash, and here 0 to 0 and 1 to 0, so we have taken it f equals 0, and whereas in the final one we will get 0 to 1 and 1 to 1, so we have taken f to 1, f equals 1, and this is the truth table for 4 to 1 line multiplexer. And in 8 to 1 line multiplexer, it is a device that selects one of 8 data inputs into a single output line. And this is the actual program for the 8 to 1 line multiplexer. And module, I have taken MUX and S and D, and as I have said before, S stands for selector and D is the data and Y will be the output. And input will be taken in the 2:2 ratio for the selector purpose, and for the data type input 7:0. We have taken in the ratio of 7:0 for the data, and whereas y will be the output, where is stored in the reg, right? And in order to check the condition between S or D, selector or data, we use the condition always S or D, and with by checking to the case S, in the case 0, the output y with the data 0, and in the case 1 with the y data 1, and in the case 3 y output with the data 3, and in the case 4 y with the data 4, and even with the case 5 with the data 5, and even finally with the 6 with the output y with the data 6, and at last 7 with the output y with the data 7, and the case will get finished at here and the module will be get closed. And this is the output for the final, this is the output for the 8 to 1 line multiplexer, and this is the truth table for the 8 to 1 line multiplexer, whereas we have divided the truth table into 8 equal parts, and this for stands 0, first, second, third, fourth, fifth, sixth, seventh, into us 8 cases, different types. Here we can see it stands for 0 to 0 and 1 to 1, so we have taken directly into the D, and here 1 to 0 and again 1 to 1, so F equals D, and here 0 to 1 and again 1 to 0, so F equals D dash, and again here 0 to 0, 1 to 0, so again F equals 0, and here again 0 to 0 and 1 to 0, so F we have taken as 0, and again here 0 to 0 and 1 to 1, so F equals D, and here again if 0 equals 1, 0 to 1 and again 1 to 1, so F equals 1, and here again 0 to 1 and again 1 to 1, so F equals 1. And in first case, this is the first case, F equals D, F equals D, so we have taken directly as goes to the upper side, and again in the case 1 we have taken to the upper side and directly it takes goes to the upper side, and but in the second case, yeah, we can see in the second case, as we have the D dash at here, so we have taken not. in order to indicate the D dash, and again 0 0 as it in the third case and fourth case we have taken to the 0 upper, and again D, whereas D directly it stands for direct data. We are in the case 5 we have taken it to the directly upper side to the D, and again f equals 1 we have taken it to the upper side 1. Thank you, friends.
Good morning, everyone. My name is Kiran P. Today, my topic is demultiplexer. It is a lab program of demultiplexer module demultiplexer standard DMX X, D, Y, SRD, SNDR inputs and Y is out input S of 1 is to 0 is a select lines of 0 and 1. Input G, output 3 is to 0, Y is a here 0, 1, 2, 3. Register Y is to 0, Y always at SRD begin Y of 3 is to 0 equals 0. Case of S, case of 0 is 0 is to Y of 0 is equal to D. Case of 1, Y of 1 is equal to D. Or case of 2, Y of 2 is equal to D. Or case of 3, Y of 3 is equal to D. With the output, the select lines are 0, 0 or 0, 1 or 1, 0 or 1, 1. Input is P equals 1 with the output 0, 0, 1, 0, 0, 1 or 0, 0, 1 or 0, 1, 0, 0, 1, 0, 0, 1, 0, 0. Thank you, guys.
Hello everyone, myself Manojar. Today I am talking about flip-flop. Flip-flop is a digital circuit that stores a single bit of binary data, either 0 or 1, and can switch between two stable states. And this is the 8th one program of DDCO Lab Manual, that is Design Verilog program for implementing various types of flip-flops such as SR, JK and D. First one is D flip-flop. This is the Verilog code for D flip-flop. I am taking DFF for a module name. D is data input, Q is the output, QB is the complementary output of Q. CLK is a clock signal, RST is a reset signal. These two lines are the input ports. Input is data, clock, reset. Output is Q and QB. Registers, this is the register port. Register Q and QB means Q and QB registers are storing the output of the given inputs. This is the always block. Always clock is triggers, then program execution starts. If reset value is 0 for synchronization reset, else case for D starts when input 0, when input is 0, output is 0. When input is 1, output is 1. Here the case is ends. Assigning the QB equals inverse of Q. QB is because QB is the complementary output of Q. Here is the D flip flop module sends this, and this is the output of D flip flop. I'm giving data line is 0, clock is 0, reset is 0. This is the output is shown in graph in milliseconds. Next is SR flip flop. This is the Verilog code for SR flip flop. I am taking SRFF for module name. SR is in S and R is input. Q and QBs are output. QB is a complementary output of Q. CLK is a clock signal. RST is a reset signal. These two are the input ports. Input S and R, clock and reset. Output is Q and QB. Registers are Q and QB. This is the always block of SR flip flop. Always clock is triggers. Then program execution is begins. If reset is value 0 for synchronized resets, else case of SR is starts. If input is 0 0, there is no change. Input is 0 1, output is 0. Input is 1 0, output is 1. Input are same one like 1 1. It's a invalid input. There is here the case is ends, assigning the QB equals inverse of Q, because QB is the complementary output of Q. Here the SR flip-flop Varela code is end. This is the output of SR flip-flop. S value 0, R value 0, clock signal is also 0, reset is 1. Here the output of the given input. And next one is a JK flip-flop. Here I'm taking JKFF for module name. Inputs are J and K. Q is original output. QB is the complementary output of Q. CLK is a clock signal. RST is a reset signal. These two lines are input ports of the input ports. Input is J, K, clock reset. Output is Q and QB. And registers also Q and QB. This is the always block of the program. Always clock is triggers if reset value is 0 for synchronized reset, else case JK starts. Input is 0, 0. When input is 0, 0, there is no change. Output is no change. When input is 0, 1, output is 0. When input is 1, 0, output is 1. When input is 1, 1, output is inverse of Q. Inverse of Q or toggle means outputs are changing. Outputs are changing. Here the case ends, assigning the Q and QB equals inverse of Q, because QB is the complementary output of Q. Here the JK flip-flop Varela code ends. This is the output of JK flip-flop. When J input is 0, K input is 0, clock signal is 0, reset value is 1. This is the output shows in the milliseconds. Thank you.